In this video, we're going to continue our discussion on confidence intervals to look a little beyond what we've started with the basics and also talk about how they behave when certain parameters and statistics change. So we've been previously estimating kind of our mystery mean, our mystery population mean, by constructing a confidence interval using the sample mean, the sample standard deviation, and a confidence level, and we really focused on the 68, 95, 99.7 rule, looking at confidence levels where the percentages fell exactly 1, 2, or 3 standard deviations away from the mean. But that's not really realistic. Those aren't numbers that we would normally use for talking about confidence levels. So we're going to take it a step further today to say what happens when we want a different confidence level. For example, if we wanted a 90% confidence level or a 99% confidence level, how would we calculate that? Well, first let's remember what we're exactly doing here. What we're trying to do is find some number, and we're calling it here a standardized value of that number, z star, but some number that between the same numbers of standard deviations above and below is going to achieve some confidence level or probability under the curve. So we want to be able to say that, using our sample mean, we are a certain percentage sure that our population mean falls within this area. So what is the probability that our population mean actually does fall within this certain number of standard deviations of the mean? And that certain number of standard deviations, when standardized, we're calling that z star. Another word for that is called a critical value. So when you see critical value or z star, that's what we're going to be talking about here. So to calculate a confidence interval from mu, we use the familiar formula. We're familiar with the fact that we start with our estimate, which is our sample mean. We're estimating that our population mean will be the sample mean plus or minus some margin of error. And now what we're going to be doing is in the margin of error, before when we said, for example, 95% sure, we knew that that was 2 standard deviations away. So we would say 2, the critical value would be 2, times the standard deviation of the statistic. So we had our estimate plus or minus 2 standard deviations as a margin of error. But the critical value isn't always going to be a very simple number like 1, 2, or 3 that we've been using so far. So how are we going to find that? As an actual example of what we've been doing with the 95% confidence level, if we had a sample mean of 150 and a sample standard deviation that we calculated of 10, and we want a 95% confidence level, we would know that our estimate would be that the population mean is the sample mean, plus or minus 95% we know is 2 standard deviations away, so 2 times the standard deviation of 10, which is 150 plus or minus 20. So in contextual terms, we would say that we are 95% confident that our population mean will fall between 130 and 170. But as we mentioned, our critical value isn't always going to be a nice even 1, 2, and 3 standard deviations away from the mean. So we're going to actually use a new table called a confidence level table with critical values, which in our book is going to be at the bottom of table C. There's one row at the bottom of table C, and within the unit in our book we do have sort of this mini version of that table, so that we can see we have values for 90, 95, and 99%, which are the 3 most common confidence levels that we'll typically use. Now as we take a look at this, we'll notice we've been using a confidence critical value of 2 for 95% because of our 68, 95, 99.7 rule. But remember, we talked about in the past that 1, 2, and 3 standard deviations was just an approximate number. So in the critical value table, you'll actually see instead of 2 for 95%, you'll see the more precise number 1.96. And then they also give us the z score, the z value for the 90% confidence interval and the 99% confidence interval. So these numbers here, these critical values, represent how many standard deviations away from the mean is our confidence interval going to be to achieve this confidence level. So, you'll notice here that a 90% confidence level is going to be closer to the mean. 99% confidence level is going to be further away from the mean. So you can look up these confidence levels on Table C, as I've recommended. You might want to add them to the top of your Table A if you have a printed version of that you're referencing frequently. So to sort of summarize that in a more formal way, the confidence interval for the mean of a normal population means that you've chosen a simple random sample, and you've done it scientifically using the randomization techniques of size n from a population having an unknown mean mu and a known standard deviation sigma. A level C confidence interval for mu is the following formula. And you would find that z star, that critical value, from the standard normal distribution. And again, it's been calculated for you in the Table C. And the way we would construct this confidence interval is, again, we take our sample mean and we use that as our estimate for our population mean. And then we want to know how many standard deviations away from the mean does our confidence level encompass. So whether we were choosing 90, 95, 99.7, that would be the number you would insert here for the z star. Not the 90, but the value for 90. For example, if we wanted a 95% confidence interval, we now know that we should use the number 1.96. And we want that times the standard deviation of the sample. Remember, we're looking at a sample estimator, and therefore we need to use the sample standard deviation. But rather than using a symbol here for the sample standard deviation, they've taken the multi-step problem that we've done before, calculating that standard deviation first and then putting it in the formula, and just built that into the formula. So we know that sigma, the standard deviation for the population, divided by the square root of n, is our standard deviation for the sample. So this builds all of it into one formula. So if you know the confidence level, you know the sample mean and the standard deviation for the population, you can just plug all the data into this formula and go directly to the confidence interval. You don't have to do a second step, an integral step of calculating the sample standard deviation. So if we were to look at an example of what this would mean and how to use it, again, our estimate plus or minus the critical value, that's z star, times the standard deviation of the statistic. So what this is showing graphically is, here's our values of x, here's our mean, which we don't know for the population. Here's the sampling distribution of x bar, but we're going to assume that the mean of that sampling distribution is the mean of the population, plus or minus some standard deviation defined by our critical, our confidence level. So plugging it into the formula, we have x bar plus or minus z star times sigma over square root of n. So in this example, we have a mean of 240.79 plus or minus, we're trying to do a 95% confidence interval, so we're going to use the 1.96 times 20, which was the standard deviation for the population, divided by the square root of 16. There must have been 16 people in this sample, which ends up giving us a confidence interval of 240.79 plus or minus 9.8, which translates, this notation here is kind of shorthand for saying that it falls between 230.99 and 250.59. You should really get into the habit of writing that out longhand so that you really can see the interpretation of what we're talking about. So kind of going through the four-step process as it applies to confidence intervals, we want to state what is the practical question that requires estimating a parameter. Remember, a parameter is a population value, so the parameter that we're estimating here is the population mean. We want to identify that parameter, choose our level of confidence, and select the type of confidence interval that fits our situation. We're going to solve by carrying out the work in two phases. first we're going to check the conditions for the interval that you plan to use. So what this really means is making sure that we have a simple random sample, that it, there really is a normal distribution, all of these things that we talk about in the textbook, which for the most part we're just making the assumption that that is true in our problems. Calculate the confidence interval, identify the confidence level, write down the sample mean, the population standard deviation, the size of the sample, and use our formula for that. And then return to the practical question to describe your results in this setting. So don't just write down the number, but actually summarize the results in the context of the problem. So now that we know how to calculate a confidence interval for any percentage range, basically, of confidence level that we may want to define, we want to start talking about how confidence intervals behave as some of the parts of that formula, some of the statistics within the formula change. Because it's not always just going to be, here's the data, calculate the results. Sometimes we need to, you may find yourself doing this in order to determine what size sample do you need to achieve the purposes. So the Z confidence interval for the mean of a normal population illustrates several important properties shared by all confidence intervals. So the user chooses the confidence level and the margin of error follows. So the margin of error comes from that confidence level that you're choosing. In general, we really would prefer to have very high confidence level, but a small margin of error. It's not really a lot of value if we say that we are 99% sure that the mean falls 100 plus or minus 75. That's a very wide margin of error, and so it's not really that useful. Even though we're 99% sure, it's such a wide margin of error, it's not really that useful in practical uses. So we not only want high confidence, but we want a small margin of error. And there are things that you can actually do to create that kind of a situation when you're designing an experiment. The reason we want that high confidence suggests that our method almost always gives correct answers. So, again, viewing this from the perspective of somebody conducting research, whatever methodology you're using to collect your sample or to administer a treatment to a group or whatever your research is, high confidence suggests that the method is sound. And the small margin of error suggests that we've pinned down the parameter very precisely. We want to be able to predict the mean as closely as possible. So how can we sort of get a small margin of error? So we're going to do this by looking at the margin of error portion of our confidence interval. So we're taking away that estimate plus or minus piece and just looking at the margin of error piece. And we have three components there. We have the Z star, which is our confidence level. It comes from our confidence level. We have sigma, the standard deviation, and we have the size of the size of the sample. So we want to look at what happens as we change each one of those to see if could we change one of those to decrease our margin of error. So the margin of error gets smaller when, well, let's look at Z star. The smaller Z star gets, the smaller a number that Z star is, we're going to get a smaller margin of error, because whenever you multiply something by a smaller number, it's going to be smaller than if you multiplied it by a larger number. So, keeping in mind Z star is standard deviation, how many standard deviations away. The smaller Z is, the fewer standard deviations away it is from the mean. So we've got a tighter confidence interval there. Now think about what happens with standard deviation. Well, it's the same type of thing as the Z star. Standard deviation tells us how variable our data is. So the smaller the standard deviation is, the closer our data approximates the mean. Remember the sampling distributions that we were talking about. When they get very, very tall and skinny, all the values are closer to the mean. So therefore a small standard deviation is going to result in a small margin of error. Now the one that's a little trickier to think of, but actually kind of makes sense based upon our knowledge of the law of large numbers, n is in the denominator of the fraction here. So remember, whenever you divide by larger and larger numbers, it actually makes the value of that fraction smaller and smaller. 1/2 is larger than 1/4, which is larger than 1/8. So as that denominator gets larger and larger, the fraction value is smaller. So the larger your sample size, the smaller that fractional part of this formula is going to be, and therefore the smaller your margin of error is going to be. It does make a note here, since n is under the square root sign, we actually have to take 4 times as many observations to cut the margin of error in half. So if you go from a sample size of 10 to a sample size of 100, you're going to see your margin of error shrink. And again, the law of large numbers helps us to identify that's because the larger the sample size, the more predictive the sample mean is going to be.